Number 9. Number 9. Number 9. Welcome all to Math Tidbits number 9. Today what we're going to do is tackle the question of approximations. Now, by approximations, what I'm not talking about are estimate type problems where we have to estimate various parameters. What I'm talking about is an act of simplification that we often do in physics, where we want to take advantage of the characteristics of the mathematics and simplify the algebra in some cases by making an appropriate approximation, and we'll talk about how to do that in a bit. We also might be able to discover the leading behavior, I'll put that in quotes because it's kind of physics jargon, or math jargon for that matter, of a system. What's the principal thing that characterizes the way that this system behaves? A lot of times this will come about because of the ability to neglect certain small parameters. So looking for or being able to put problems in terms of certain parameters or combinations of parameters that are small, and thereby be able to neglect them at some level. This will also be important in our considerations. Okay, in order to get there, in order to bring forth the most common sort of approximation that we do in physics, we're going to be talking today about the binomial expansion, and Taylor series. Now, in a large part, this is simply an information item kind of video today. We're really going to be highlighting some of the things that underlie commonly used approximations. And so I want to give you all of that groundwork. To do, or to sort of couch this whole narrative, I'm going to put it in terms of the grandfather clock as an example. So grandfather clock, I think there are actually grandmother clocks too at some level, but the grandfather clock uses a simple pendulum at its core that has nice property of a repeatable period for its oscillation, and therefore you have the ability with gears and such to run a clock on the basis of a simple pendulum. Well, the period of a simple pendulum is equal to 2 pi times the square root of the length of the pendulum over g. So we're imagining here a pendulum that has length L0 that's in the gravitational field of the Earth or the Moon or Mars or what have you. We can use different g constants that we would calculate for various places, which I often like to do in giving pendulum problems. This is the behavior, the period of a simple pendulum under certain conditions that we'll talk about when we get to pendula in class. But one of the things that's really important for a clock is that value L0 has got to be stable. Because if it's not, then the period isn't going to be constant. Okay, if it's not, then the period will not be constant. So we have to consider, or it's useful to consider, what happens if the length does lengthen a little bit. And we're really kind of interested in a really little bit. What happens if it stretches? Well, what happens if it shrinks because it becomes cold, and the pendulum string is made of wire, some metal wire. What happens to the period if L stretches or shrinks? So by way of getting to a discussion of approximations, I've chosen this example because it allows us to talk about the effect of small changes in this length. So let me show you what I mean. What's delta t going to be if L changes by little l, which is much less than L0, L0, the original length? Well, I would just write delta t as 2 pi times the square root of L0 plus L over G minus 2 pi times the square root of L0 over G, right? Here's the original, and here is the new period. So if I want to make this a little bit simpler expression, what I can do, although maybe you would argue with me as to whether this actually is making it simpler or not, suppose I take that L0 and factor it out, leaving behind a 1 plus little l over L0, whole thing divided by G, minus 2 pi times the square root of L0 over G. Now I have an overall factor, 2 pi times the square root of L0 over G, that then I can pull out of each term, leaving me with 1 plus delta, the square root of 1 plus delta minus 1. Now delta we're just letting stand for little l over L0. Okay? So if little L over L0, or if delta is a small number, I'm going to be able to do something to simplify this. And it may turn out to be really, really, really important to simplify that, because let me just give you an example. Suppose L0 was 10 meters. And let's suppose that little l, that little stretch that that the pendulum string underwent for whatever reason. Maybe it's aging, it's just getting older, or maybe it got warmer outside by a little bit, and little l changed by, let's say 50 microns. Well, delta would then be a relatively small number. Okay, delta would be 5 times 10 to the minus 6th. Some calculators that y'all might have may not be able to figure out the difference between the square root of 1 plus 5 times 10 to the minus 6 and 1. So it may be that we really ought to use an approximation here. So let's try to figure out what that approximation is, won't we? In order to get there, I need to take up a little musical interlude on Taylor expansions, or Taylor series. Okay, so we're going to get there right now. So Taylor series. Taylor series are very important, or let's say expansion. You will find yourself using this throughout your years, as in physics, in mathematics. It's really, really handy. So let me first describe a fact. Most functions of a single variable, or I should be coy and say many, can be written as a power series, namely f of x equals a naught plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth, and so on. And so if we want to think about particular functions, we need to get a handle on what these constants are. So one of the ways to get a handle on what these constants are is to figure out, to look at the function f at special places where we can highlight the behavior of each term, or eliminate the behavior of each term, I guess, and focus just in on one. Well, one of the things I can do is I can take f of 0. F of 0, this is a power series, right? So it's just in each term is a power of x times some constant. Well, if I evaluate at 0, all of those terms to the right of a naught go away. So it's just a naught. So now I already know that a naught is the value of the function that we're interested in at 0. Now, by the way, f of x could be anything. Could be sine x, could be e to the x, could be natural log of x, could be any number of things that we're going to try to approximate by a series. Okay, so if I wanted to know what a naught was, I just need to evaluate my function at 0. So for instance, if the function that we're interested in is sine of x, then we know that the power series that results has to have an a naught term of 0. That will turn out to be important, actually. So what if I want to know something about the next term? What if I want to know a1? Well, it might occur to you that I can isolate a1 by taking the derivative of f with respect to x. Derivative of f with respect to x is a naught goes away, a1 is left behind, and a2 is accompanied by a 2, so 2a2x plus 3a3x squared plus 4a sub 4x cubed, and so on. If I evaluate at 0, so I'm going to call this f prime. That's just another notation. So f prime at 0 is equal to a1. And likewise, then, what if I take the second derivative? That's f double prime. That's d squared f dx squared. That's going to be, I'm going to drop the a1. I'm going to be left with a leading term of 2a2. I'm going to drop a 2 down here to make this 6a3x plus 12a4x squared, and so forth. If I take f double prime at 0, I'm going to get 2a2. So that a2 is 1/2 f double prime at 0. And then you can see, I'll just let you do this in your head. If I take f triple prime, that's the third derivative of f with respect to x, and evaluate it at 0, this term is going to become 6a3 when I take the next derivative. Will not be proportional to x, but all the rest of the terms to the right will be, so this will be 6a3. In other words, a3 is 1/6 f triple prime of 0. That turns out actually to be 1/3 factorial times f triple prime. All right? So the beauty of this is we now have a means, and I just evaluated at 0 so I could get rid of all those other terms and zero in, no pun intended. I hate it when I do that. we can zero in on, focus in on one particular term. So this simply becomes f of 0 plus f prime at 0 times x plus 1 over 2 factorial f double prime at 0 plus 1 over 3 factorial f triple prime at 0. Sorry, I'm missing an x squared there and an x cubed here. All right? But it has a very nice appearance. Okay? This is of interest for looking at f of x with x small. All right, I can come up with a more general case if I want to know f of x where if x is near a, then I'm going to replace 0 by a and replace x by x minus a over here. That should be f of a, or f prime of a times x minus a, 1 over 2 factorial times f double prime, f of a times x minus a squared plus 1 over 3 factorial f triple prime at a times x minus a cubed, and so on. So that's the general expression for expansions around a point near some finite value, some value of x equals a. This is very, very useful to know, this idea, this concept of a Taylor series. Okay? So Taylor series, perhaps you've done it in math before, but really, really critical and very, very applicable in physics all over the map. All right? So now I want to go back to our problem. Okay? Go back to our problem and remind ourselves of what we're trying to do. We're trying to deal with delta t equals, call that t naught because that's what it is, right? That value is t naught. So it's t naught times the square root of 1 plus delta minus 1. All right, that was what we were looking for, what we were looking to do or accomplish or approximate. So I'm going to say, let's take a look at, suppose f of x is 1 plus x to the nth power, a binomial, which we will then raise to a power. And let us look at what happens as x goes to 0, as x is really small. So we're going to want to use the form of the Taylor expansion, or it's actually called a Maclaurin series for those trivia buffs. I doubt it will be useful at Thursday night trivia at the Courtyard and Cellar, but maybe. We're going to take the Maclaurin series. We're going to expand this function around x equals 0. So let's note here that f of x is 1 plus x to the n. I don't know why I wrote this. F prime of x is going to equal n times 1 plus x to the n minus 1. F double prime of x will be n times n minus 1 times 1 plus x to the n minus 2. F triple prime, we won't go there, but that's going to be n times n minus 1 times n minus 2 times 1 plus x to the n minus 3. All right? And therefore, the function f of x can be approximated by f. Let's just remind ourselves again. It's f naught, or f at x equals 0, plus f prime at x equals 0 times x, plus f double prime over 2 factorial evaluated at 0 times x squared, plus f triple prime over 3 factorial, evaluate f triple prime at 0 times x cubed, and so forth. And now f of 0 is going to be 1. F prime of 0 is going to be, let's look here, f prime of 0 is going to be, this is going to be 1 raised to any power is 1, so this will be n. F double prime of 0 will be this guy. That whole thing is 1, so this will be n times n minus 1. F triple prime at 0 will be, as you can guess, n times n minus 1 times n minus 2, and so forth. And so what we get is the binomial expansion, which looks like f of x equals 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus n times n minus 1 times n minus 2 over 3 factorial x cubed, and so forth. Very famous binomial expansion. Okay? Now, for our example, what do we have? For us, n equals 1/2. Well, you know what? It actually turns out that this works no matter what n we use. N doesn't have to be an integer. So let us then see what f of x looks like. F of x, which will be for us 1 plus x to the 1/2. We will write this as 1 plus 1/2 times x plus 1/2 times 1/2 minus 1 over 2 factorial times x squared plus 1/2 times 1/2 minus 1 times 1/2 minus 2 over 3 factorial times x cubed, and so forth. We can simplify these down as 1 plus 1/2 x. 1/2 times, that's minus 1/2, divided by 2, that's going to be minus 1/8 x squared, and then this will be 1/2 times minus 1/2 times minus 3/2. We got a half and a half and a half and a half. We got a 3 up top. You can do this as well as I. This will give us a factor of 1/16 x cubed, and so forth. So we have several terms, and depending on how small x is, we keep a certain number of terms. Okay? It may be that we keep only the first term, 1, or we keep, first term would not be very interesting, right? Or we keep the second term, depending. All right? Let's write this out in general, though, at least out to the third term. Delta t is equal to t naught times, now we got the square root of 1 plus delta. So this will be 1 plus delta over 2 minus delta squared over 8 plus delta cubed over 16 minus 1. We'll put a little approximation sign over this because it's only good out to the third term. And therefore, it is equal to t0. The ones cancel, which often happens in this kind of expansion. T0 times delta over 2 minus delta squared over 8 plus delta cubed over 16. And so forth. You can see those terms are getting smaller and smaller and smaller. All right. Let's check what happens if we keep only the first term. So keep first. For delta t, therefore, is equal to t naught, approximately equal to t naught times delta over 2. And let us suppose we have a 1.000 meter long pendulum. And let us suppose that it grows in length by half a centimeter. So L naught equals 1.000, and L equals 5.0 times 10 to the minus 3 meters. Okay? That means that the period change as a fraction of t naught is delta over 2, and delta is 5.0 times 10 to the minus 3 meters divided by 2 times 1.000 meters, right? So this would be 1/2. Delta is 5 times 10 to the minus 3 meters divided by 1 meter. And in other words, this is 2.5 times 10 to the minus 3. So, 1/4% of period change. Well, that's not all that much. Let's see how important the second term is, though. Okay? Can we do that? If we see how important the second term is by calculating it actually, let's just calculate delta t out to that next term. So delta t, or rather calculate delta t over t naught, to the second term will be delta over 2 minus delta squared over 8. Am I right? And delta we decided was 5.0 times 10 to the minus 3 divided by 1.000. Okay? So that if I calculate delta over 2 minus delta squared over 8, I'm going to get something very close to what I just got. 2.4969 times 10 to the minus 3. So this is compared to 2.5 times 10 to the minus 3. It is only different by about, this is different by about 3 parts in 2,500. Okay, so it seems to me that the second term isn't really needed, and we can just approximate based on the first term. Anyway, all this to say, there is actually a lot of good, a lot of utility in doing this kind of approximation work. Now, one last thing. This will not be required of you at all, but to prove these things, although again it's useful, some common expansions. So we've already given you one, the binomial expansion. Some other common expansions that we run into and that are worth knowing, although you can always calculate them, right, would be e to the x. Well, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. The sign of x. This will definitely come up against when we talk about pendula and their behavior, what x for a pendulum or any simple harmonic oscillator looks like. It will turn out to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. You get the pattern. And cosine, likewise, is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Again, I bet you can discern the pattern there. These three expansions will be very, very useful. Oftentimes, for small x, we will be able to approximate e to the x as 1 plus x, or sine x as x, or cosine x as 1 minus x squared over 2. In fact, you already saw this in a previous video if you had taken advantage of it. All right, that looks like to me enough for today. Thanks for joining, and we'll see you next time.